Okay, so for today's lecture, I would like just to continue, finish off what we have discussed last Friday, and maybe having more examples, one or two examples, maybe one example, and then continue to next sections in our chapter 15.9. And if we finish 15.9 by today, then next Friday will be about just reviewing uh, um, some problems. We're reviewing some problems in class, especially uh, about chapter 15. And if there's nothing left, if there's nothing left for a discussion, uh, I think we still have one more quiz and one more final exam. So one more quiz will be about this week. So maybe around weekend, I will prepare a quiz, and perhaps the another schedule will be um, for the final exam. It probably 6th of June, like probably the easy schedule. Let me check whether it's possible. The uh, quiz deadline. Yeah, perhaps the quiz deadline. I will announce maybe this week, and maybe I think 4 5 days. Is it enough for 4 days from the weekends? 4 days or 5 days. So the deadline will be around Wednesday or Thursday. So suppose uh, the announcement on Saturday, and you will maybe having a deadline on Wednesday. I'm still preparing the platform for the quiz. Perhaps I will use the new platform for this quiz and just to try um, whether it's really good or maybe having some trouble for the platforms. Because I will use the same platform for the final exam. So I think I will just need you to familiarize with the platform. Okay. Okay, I think we can start our course. Okay, so if we can finish all sections by this week, then we finish our class. Okay, and next week will be no class if we finish by this week. So next week will be no class. You just wait for the quiz, wait for the final exam. Okay, a quiz will be this weekend until several days, and then the final exam will be 6th of June. Okay, perhaps 6th of June. Okay, I think that's okay. Yeah, Blessing. What would you like to ask? Yeah, do you have any questions, Blessing? Some of the question will be identical. Some of the question will be identical. Okay, some of the question will be identical. So I think you can also working the quiz. Um, just make it as your exercise also to prepare a final exam. Okay. Okay. I think we can continue for this part. So last Friday we have discussed about this sphere, the spherical coordinates, and how to integrate a sphere by triple integrals. As you may see, that we have this conversions. Okay, so the first thing is we convert the Cartesians x, y, z into the spherical coordinates, which is the spherical means that we have the radius, the angle theta, and the angle sine. And then we have this additional additional symbols, additional conversions, that is the radius squared, sine, phi, and then all the x, y, z are really converted into the spherical coordinates. Okay. Now, in one example, uh, we have this in our discussion, and how do we know whether it is a sphere or not? Is from this. I think the most obvious one is this: x squared plus y squared plus z squared. This is a sphere, and by that equation, we know that we can convert this into our radius, and then if there's nothing left in the information, then we just assume that the theta is as usual. The full circle theta is 0 to 2 pi, and the psi will be 0 to pi, because that is the full angle that the equation might have. So this will be our triple integral, and this will be the conversions from the E, and we have another additional rho square sine psi. Okay, and then we just take it like usual, we integrate, and we got this result. Now the second question that I have at the end of the class last Friday is how to find the volume that is above this z equals square root of x squared plus y squared and below a sphere. So we have a cone. Okay, so we have a cone like I think this is the shape like an ice cream. Because we have a cone and you have a sphere above. Okay, so you can actually quite imagine because this z is the axis of the cone. So you have if we draw. I forgot to attach the picture, but let me just draw quickly. This x, y, z. So we have a cone. So perhaps a cone around here. Okay, maybe around that point. And a sphere around here. Okay. So because x squared plus y squared plus z squared equals z, it's supposed to be, if we could finish off uh, the sphere, well, we can write this as x squared plus y squared plus, we could write this z squared minus c equals 0. And we could write down that x squared plus, sorry. Or maybe just let it slide here. I think we can just say that this will be 0, 0, 1. This will be z equal x squared plus y squared. And we can solve this. I think the center will be changed to half, right? From this z. So z squared minus z plus 1 over 4, right? We can write like that. And we can see this will be c minus half, right? It's too messy. Let me just clear this mess. We could write x squared plus y squared plus z squared equal plus 1 over 4, right? So rho is half, and center is 0, 0. I think that will be better. So center here, this is half. Okay. Okay, now, because we know that this is include the sphere, we can convert. Okay, we can convert the Cartesians into spherical coordinates. Okay. So first, we could write down sphere is rho, z is rho sine psi, right? And rho cosine. Sorry. So we could maybe right here. Y squared plus z squared is supposed to be rho squared, but here our z. So z is square root of x squared plus y squared. Okay. So we could write down that z is, we could write rho squared as rho cosine psi. Z is rho cosine psi, right? Or we could write down that rho is cos psi. And now we can exchange this x squared plus y squared. So rho cosine psi equal, it should be a little bit longer, so let me move a little bit left. So the x will be rho squared sine squared psi cos squared theta plus rho squared sine squared psi sine squared theta. Okay, now we plus this, and cos squared theta sine squared theta is 1, right? So we could have just rho squared sine squared psi, and rho cos psi is equal rho sine psi. Now we can finish off this. Okay, we can cancel. So we have tangent psi is 1, or in by the descriptions of this E, this solid E, the psi or the angle is pi over 4. So when they are having the intersections, the psi is pi over 4. Or we can write down the whole interval for E. So rho, theta, and psi. Theta is from 0 to 2 pi. For psi is from 0 to pi over 4. And for the rho is cosine psi, right? So rho is cosine psi. And that will be our integrations for the interval. It should be equal. Sorry, forget to write. Okay. Okay, after we convert all to sphere and then writing all the interval, okay, we could take this into our integrals. Okay, but let me just wait for a few minutes for you to collect all the information. Okay. If there's anything that you miss, maybe having some confusion on this one, let me know. So firstly is to describe the sphere. What is the radius of the sphere, and then the center of the sphere to make sure that we are in the correct positions to confirm that the sphere is correct. And then, of course, because we have two shapes, the cone and the sphere, then they are both will be having some intersections, right? So that is how we get the angle and also the row itself. Okay, I think we can continue. Okay, so we can continue to integrate the uh, volume for the solid E. We can start by writing down the cos sine, right? And then rho squared sine sine d rho d psi d theta. Okay, for theta and psi, we can just switch each other because I don't think that is very having very significance. But I think depends on you. Sometimes it's easier to have theta first. Sometimes it's easier to have a psi first. Okay, it depends on the questions also. Okay, we can take it into our calculations. 2 pi directly theta, and the inside we can directly get that rho cube over 3 sine sine d sine. Okay, so this will be 2 pi. Maybe 2 pi over 3, the 3 going out, and then sine psi oh sorry, I forgot to make this cos sine. So we get cos power of 3 sine sine sine. Okay, we need to integrate this. Okay, integrate this to. I think you can directly type in into your calculators. I think that's still okay for me because it's just a single integral, and this is supposed to be 2 pi over 3. This will be minus cosine 4 sine over 4, or you could take it into substitution if you want. Cos sine, and then the u will be negative sine sine. or you could take it in with different way. But I think this is what we can do. And then substitutions. So use substitutions, and this is the result. Because pi over 4 is 1 over square root of 2. Squared will be half, and then square will be 1 over 4. So it will be 1 over 16. So 1 over 16, and 0 is 1 over 4. So 1 over 16. So negative 1 over 16 minus 1 over 4. Supposed to be 3 over 16. It's supposed to be 1 over 8, right? I think I can erase this. Okay, I think that will be the answer. Okay, any questions? Any questions? Zero to cos phi. Cos phi is from here, from this, from here. Because the total conversion for the x squared plus y squared plus c squared for sphere is always having a rho square, right? And we know that this our equation is having z, and z is having rho cosine phi, right? So we could say that rho squared, rho cos phi, and we can write this here. Okay, is that clear, Evander? So perhaps my suggestions to give you um, insightful, more insightful for all the conversions. Before you start to convert all the things here, you could write down the conversions first. So we could write rho z is rho cos psi, and then x is blah blah blah, y is blah blah blah, and maybe x squared plus y squared plus z squared is rho squared. So you can write this 4 first, and then through this 4, you could see how you could connect with each other, take some relation with each other, and then make some cancellation and becomes new equations, okay, or new conversions. 1 over 2. Yeah, we don't use the 1 over 2. Because if we are using 1 over 2, then we having how to explain this? Let me explain. This is a sphere, right? If I draw the sphere, okay, so I want to use the 1 over 2, I need to have a full sphere, right? Did you get my idea here? And because it is a spherical, we need to connect each variables. Okay. So what variables connection means is we need to relate each variables. Okay. For example, we need to relate theta and psi, and then the rho. Uh, we need to have all the interconnections that might happen. So if we look here, the sphere that we are observing is having a half sphere and then having another cone. Having another cone. So if we use the 1 over 2, from 0 to 1 over 2, then it should be a full circle, right? A full circle of sphere. Okay. Maybe giving you more practice. One example. Let me check the example. Okay, let me give you this one. Evaluate the iterated integral. So evaluate it. Iterated integral. Evaluate the iterated integral of and E is described in the picture. Well, another thing, I just remember the obvious one reasons for uh, but telling the radius or telling the interval for integrals in the sphere, if you see any equations like this having a constant 4 and a constant 9, suppose you are writing the triple integrals because there is no change in the center for the sphere. So for sure, the endpoints, the interval, it should be a constant. Okay, it should be a constant too. So the question for Fando, you can actually see what the equations for the sphere that is given. If it is a constant, then the interval is probably constant. Okay, most cases that it's all actually a constant. But if you have a full equations and then it's mentioning that it's shifting its center, then you don't really need to use the. And I think if you use a constant, it will be giving you a different shape, a different shape from the actual shape. But if this happens, it means that you have the radius 2, you have the radius 3, okay? And that will be your interval for integrals, okay? For integral. Okay. So what we are going to evaluate is we are going to evaluate these functions as triple integrations, okay? And the solid E will be defined as in our picture here. Okay, so first, because it's like 1/4 of a ball, right? 1/4 of the ball. So if I have a ball, this is just taking this, yeah, taking this one, okay, okay, and then taking it. So it's supposed to be having. So this is a full. It's 1/4 here. Okay. Okay, now if you look on the phi, okay, what will be the angle? Usually we have 0 to pi, right? Usually we have 0 to pi. But now we have, I think from pi/2, let me go through here. And also from the theta. The theta is from okay, let me write here E F X Y Z T V. Okay, this is triple integrations. Convert this into a spherical. It will be rho squared and then square root. This is supposed to be rho, and multiply with the conversions is rho squared sine psi. And then let me write the rho, the theta, the phi, and the rho will be 2 to 3, and theta will be from the pi over 2, right? Pi over 2, let me erase this. If I take this is pi over 2 here, pi over 2, let me, 3 over 2 pi. Or maybe let's make it more clear, maybe taking this, if this is a pi over 2, then this should be, if this is pi and this is 3 over 2 pi, this shape will be going over there. So it goes for pi degree, and it's from pi over 2 to 3 over 2 pi, right? So we can describe the solids. We can describe the solid rho theta phi. So rho is from 2 to 3. And then this will be pi over 2 theta 3 over 2 pi. This part here is the first octant. Okay, the first octant. The first octant means that's supposed to be the positive, all positive quadrants, right? So this will be our perception should be from this 0 pi over 2 pi 3 over 2 pi. Okay, and just if you want to take notes of the angle that we need to observe. Okay, that's for theta. And from the phi is, let me use red color. So phi should be goes through here, right? But since this is just taking like 0 is from here for phi. This is this is phi. This is phi. So this is supposed to be from pi over 2 to pi, right? For phi. So for psi is pi over 2 to pi. Okay. Any questions on how we define this angle? Any question? Everything clear? So as long as you follow this green color for theta and red color for phi, I think for all the sphere we will have this kind of at least as a standard. Will it be the same as 0 to pi over 2? You mean the same with with what? The 0, you mean this one? You mean this one, right? I think it will be a little bit different because it will be having a different subject. Because we try to describe all these variables with the coordinates. Okay, with the coordinates. I believe if we are making mistake in taking this, for example, the 0 to pi over 2, it means that it's not the one that we are calculating here. But if the volume is the same and you know that it has symmetrical, it should be okay. It should be okay because at the end the symmetry. Okay, I think if you take 0 to pi over 2, this will be the upper one. Okay, the upper one. If you if this is the below here, right? What you mean is the one that up here. Okay, clear, right? But since we are just calculating the volume and we know that's a sphere, if we cut half and cut another half, they will have the same volume, right? The same volume. Okay, then we can take this into our calculations. The theta is pi over 2, 3 over 2 pi. This one is pi over 2 and pi. And then we can solve this. This is rho cubed sine phi d rho d theta d phi. And I think for each one we have each variables, right? Oh, sorry, this one. So we can take it separately. Okay, and we can take it and integrate. Sixty-four, 65 over 4. Okay, I think the key is to get the conversion correct and to get the interval correct. That's the main key for the spherical coordinates. So I hope this perspectives, okay, to look at the theta and look at the phi, that is, I think, the one way you are going to take on, okay, for the coordinates, okay, for the theta and phi. So for the theta, the 0 is going to be the x-axis, and then for the phi, the 0 is the z-axis. Okay, this is just to help you in the future cases. But I think if you shifted the angle, as long as you shift it consistent in a consistent way, the results should be the same. The results should be the same. This is just to help you making some connections. Okay, I think you can take this as your reference for converting the coordinates. Okay, maybe any discussion, any questions? Does anyone agree for the dates for the final exam to be 6th of June? Do you have any maybe any different opinion for when the exam should be taken place? 6th of June is next 2 weeks. Is it okay? 6th of June, or you have any other options? I would like to know whether you have another exam schedule for other dates as well. If you have, you can tell me which which course you have and when is the schedule. Chemical on 8th. So do you think it's okay if 6 still okay, or you want to make it into maybe 10? Well, it depends. All right, depends on you. You can have calculus earlier or maybe 10 Friday.
Prof, how about like maybe we vote? And I think some of the students are going to prefer taking your exam first, and I think some of the students are going to prefer to take your exam after chemistry.
Oh, maybe taking vote. Do you think maybe taking vote for the dates?
Yeah, yeah, yes,
Okay,
professors.
okay, okay. Okay, I will make a vote later. Okay. Anyway, I would like to finish off the chapter 15 by this week. So hopefully the last sections by today's lecture can be at least already been introduced, and maybe a little bit having a little bit examples, so that this Friday we can focus on more on the reviews, okay, reviews and maybe a little bit of practice. Because final exam should be taken from chapter 12 to 15, but 12 and 13 will be minor, so it's mostly the majority will be 14 and 15. Okay, I think we can move on to the next sections. Okay, the last section in chapter 15 is, we call the section as change variables in multiple integrals. Or we call this change, we call this the Jacobian or Jacobian transformations. You could also say that, or just by Jacobian. I think it's supposed to be the same terms. Okay, to begin, let me just recall what we have in the calculus one. So if you have integrations from a function of f from a to b, we could transform this is what we call the use substitutions, right? Use substitutions. So use substitution, basically we are getting the x or maybe some element from our functions. Let's say if this is our making a function of u, and a is and b is g of d, and we can write another way we can write is alternative of writing these use substitutions is a b f of x dx is equal c d. This is f x u and dx du du. It's the same thing, just to make notes it having some differences in the terms and then the symbols. Okay, but it's the same thing as our use substitution. So what does it mean? Okay, what does it mean? So what we call here this transformation here, this is we call it it's a change, right? Changing the variable from x to u, right? So this is changing variable from x to u. And we also recall we also have the 15.3 and 15.8, right? This the polar and the sphere, and we have also conversions, right? In the polar we have the conversions that is let me just write this is equations, and then we change the dx dy dz or the dx dy or dy dx becomes r dr d theta, right? In the sphere we have the rho sine squared psi d rho d theta d psi, sorry, triple. Now then this has some additional r, this has additional rho sine squared, right? If you would like to include 15.7 also okay, but it's actually the same thing as polar, right? Okay, now you're getting some notes here. Okay, when we change variables in use substitutions, why we need to change the variables from x to u? Because we want to have more simplified calculation, right? We need to make it more simple. Okay, it's the same thing from these sections. That the idea for the change of variables is to make our calculations simpler. Maybe let me write in more for polar, let me write in more clear. So we have r f x y dA. This become s, and f x, oh not x, sorry, r cos theta and r sin theta. This is r dr d theta. So we change the type of the region, we change the x, y into the r theta, and then we add additional r, additional. Okay. Now generally, we can write transformation t from UV plane to xy plane. We could write as t UV equal xy, which means we convert variable u, v to variable x, y with some sort of t, some transformations, and we need to define this t. And before we define the transformations, we could let the x and y related to u and v. So we can write maybe x is a function of u and v, also y also functions of u and v. We could also write as x just x u v is also okay to write this. And we assume that t is C1 transformations. This means that g and h, the functions, is or they are continuous first order of partial derivatives. Okay, which means there is not a problem at all. So basically, this transformation say that these two functions g and h, they are continuous. Okay, what does really mean from this transformation? Okay. If I would like to draw in a more visual, which means that this is just transforming the image. Okay. Okay, let me go to the next section. So you might take the screenshots, or you want to take some notes from here. Okay. So transformations, we could just write as let's just see a point. Okay. So the left part is the UV plane, the right one is the XY plane, and our T is basically transforming a point from this S to the R. And we call this X1, Y1, and the right one is the image of point U1, V1. Get more clear, U1, V1. Okay. If no two points have the same image, this is called one-to-one. So this transformation T transform S to R. Okay, this T is transforming S to R. So the region S is transformed to region R. Okay. So they have a different axis, right? So we can call R is the image of S. So basically, from here, we would like to elaborate more on this transformation and making this transformation more general, so we could use it in any partial equation that we have, any continuous function that we have, that we can basically transform into anything according to what we are going to apply. For example, you want to transform from the Cartesians to polar, we could have some general equation that we are going to have, rather than we convert each one from x r cosine theta one by one like that. We have some general rules that we could apply. Okay. But let me just continue. And also, it has the inverse. Okay, it has the inverse, the t inverse, the transformation inverse. So if this is one to one, okay, so if one to one, then it has the uh, it has the inverse, which is t inverse, which is describe transformations from xy to u-v plane. So we could have another equations for u and v. Both are function of xy. Okay. So we could have this in terms of the inverse. Okay, maybe giving you an example, how does it work in the some simple case. Okay, in the simple cases. Let me give you an example. For example, you have x equal u squared minus v squared. So you have some relations first, okay? And then you have y to uv. So imagine you have x and y, and then you would like to know how does it relates to uv plane. Okay, if you want to construct a new plane, a new axis, which is the axis of u and v. So let's say you need to find the image of S, which is the uv plane, from u from 0 to 1 for u, and v also from 0 to 1. So we could start with u equals 0. Or we could also start from phi equals 0. And let me just, maybe phi equals 0 first. So then x will be u squared, and y will be 0. And so x is from 0 to 1 from these equations. And then let's say this becomes our, let's say, S1. So mapping the line segment from 0, 0 to 1, 0. We start with y is 0, right? 0, 0, and 0, 1. 0, 1. Okay. And let's take another conditions. And let's say we start from u equal 1. So u equal 1 will be y equal 2 phi, and x will be 1 minus phi squared. And by eliminating this, we get that x is 1 minus y squared over 4. And we know that this is a part of parabola, right? And this is given by x is from 0 to 1 also. And we also have when given maybe here, when p is 1, then this will be u squared minus 1, y equal to u, and this will be x, y squared over 4 minus 1. Okay, so also a parabola, right? Part of parabola. This is from x is negative 1 to 0, right? Or maybe we write negative 1, x, 0 for the x. And then finally, we have the u equals 0, which is having x is phi squared and y is 0. Sorry, not phi squared, minus. And that is the x is from negative 1 to 0. Now, if we take it into our picture, this is supposed to this one. Okay, so what we have here, let's say this is S1, S2, no, it should be S3, S4, S2. Oh, I think correct. This is 4. Sorry, S4. Then S2 and S3. So what we have done here is we have the relations between x and u and v. So this means that x is a function of u v, right? And y also functions of u v. Okay, and we would like to transform what we have uh, in in u v into xy plane. Okay, so into u v, we could start with having u is for example 1 0 for u equal 1, v equals 0, and then this is having u equal 1, v equal 1. So what we have here is we are going to try our best to look on what we have here for v equals 0 and u equal 1. We have this s1, so we have all this possibility here, right? And we're mapping the line segments from 0 0 to 1 0. And for u equal 1 and v equal 1, what we have here is we could have this, right? This s2 we have from here, and from v equal 1 is here. And for s4, this is for u equals 0. We start from here going down. And for each part, we can transform that this is y equals 0. Okay, this y equals 0 here, and y equals 0 again here. And the s2 and s3 is the parabola. Okay, this parabola here and parabola here. We could follow the arrow. Okay, so we start from 1, and then s2 here, s3, and then 4. Actually, if you try by yourself, trying to find out and mapping one by one, for example, just taking from 0 and then until 1, what is the possibility that you might have, and it will turns out that you can transform this s into the r by having this parabola curve, okay, in the sides here. So the image, from this s at the beginning is just 0 1 0 1 for u and v. So 0 1 1 1 and 1 0. This will be and 1 and 0 0. This will be all the vertices, right, for the square. So this is the first image that we have, and by some relations here for x and y, we could transform the s into this parabola r. Okay, any questions first? Yeah, suppose I need to show you the square first for the s, so that you can have some visuals. What is actually our discussion is about. Okay, so this is how we can transform from this interval. We transform to this region here. That's the objective, the goal. So we would like to show you that we could transform the S into R with some of transformations that we are having from this relation from X and UV or Y and UV. Okay, now similarly, with this kind of relation, we could have also in the double integral. Okay. Okay, let me go to the next section. Okay. If you have any questions, we could go back and review. And I think I will just review later in Friday also for this section. But let me go through the double integral. How this how the change of variable affects a double integral. Okay, let me give you the picture directly. Okay. Let's say we start from this S. Okay, we start from this rectangle S. And we have the lower point u0 p0, and we have the distance delta v and delta u. Okay, we have this small rectangle, and then the image of S is R, which we describe as it has a vector function. Okay, it has a vector function. So we could take this into some sort of simple equations that x squared, x0, y0 is equal to transformation of u0, v0. Okay. Okay. And we could write down the from this r. Okay, we could write the vector of uv is equal let's just define as function g and function h for x and y axis. Okay, let's just define. This is vector positions of the image of point u and v. Okay, then we could write the tangent vector at x0, y0 to this image curve. Let's start from this vector functions. So we are going to partially derive. Okay, partially derive. So this will be g u or we could write down this as dou x dou u plus dou y dou u j. And similarly, we would have also the r v is t v u0 v0 I plus h v u0 v0 j dou x dou v dou y dou v. And let me give you more image to observe. Okay, and then what we are going to do is we are going to approximate this image R. Okay. So approximate the R through the right. Approximate the image R ds by the parallelogram. By the parallelogram of this A and B. Okay. Vector A, vector B. By parallelogram vector A and B. So the vector A, if we look here, it has both has certain vector positions, right? So A is R u0 plus delta u, and v0 and minus and B and then, but we need to know that we have also a definition for this partial from this RU and RV. That is for RU, if you take the limit definition as we know in partial derivatives, and also similarly for the RV. Okay. Now from here, you could take the approximation as R u0 plus delta u v0 minus R u0 v0 is approximately the delta u multiplied with R u, and also similarly we have this is delta v and an R partial partial phi. So what is actually happens here is basically we can approximate this region R. Okay, we can approximate this region R by this two factors here, okay? By this factor A and B, which is the secant factor for the factor R and a factor position R. Okay? So what's next is, because we are discussing the parallelogram, and we have two vectors, then we might have the area of parallelogram, right? Which is the cross, okay? The cross product of A and B. If you remember the cross product in the chapter 12, the parallelogram. So we could have this, okay? We could have the parallelogram is this and this, okay? So I think we can take to the next sections, to the next page, but let me just wait for a while. You want to take some notes from here? Okay. Okay. Now from these approximations, okay, we can use this as our factor A and B, and then we can have a cross product. So let me go put the same picture again here. Then we can write from here the area of parallelogram will be the absolute value, the magnitude of the delta U RU, right? And cross product with delta phi R phi. Okay. This will be equal. The vector is just the R, so we could concentrate on R. And then the rest will be delta U, delta phi. Okay, we could focus on the RU, writing I, J, K. This is delta X, dou X, dou U, dou Y, dou U, 0. This is from the previous equation. This will be dou X, dou phi, dou Y, dou phi. Okay, it's 0. I think just two, right? So this one and this one, right? We could write this as You could write also with the usual crossing product. We could also change the order. We could also change the order like this. Same. Or we could just write this as dou x dou u dou y dou phi minus. Okay, so the definitions. So Jacobian transformation, or T, is given by x is a function of u and phi, and y also functions of u and phi. Jacobian transformations T given by this x and y is dou xy dou u phi dou x dou u dou x dou phi dou y dou u dou y dou phi. Okay, we call this the Jacobian transformations. Okay. Okay, this is just a one steps. Okay, one steps for the Jacobian itself. Because this is just this cross product, right? We still have this delta u and delta phi that we need to also make a definition. Now the area, the delta A, we could also approximate through this Jacobian. So we could write the Jacobian and multiply with the delta u and delta phi for the total equation. And to make it into our double integral, then we could imagine in a small pieces of each region. Okay. So if we have small pieces like this, okay. So this is delta u delta phi here. So what will happen if we exchange to there? Now we could have the I think I will just take into the next page later on. Okay, and have space here. Okay, you can write the essentials. Okay, for this one, you can focus this Jacobian here. So basically, what is the Jacobian? Jacobian is one transformation that you need to put on when you transform a function into another function in different variables. For example, if you find the if you want to convert from the Cartesian xy to a polar r theta, you need to transform through the Jacobian. Later, I will show you to prove that the Jacobian is actually the r. Okay. So this will be dr d theta. Okay, that is how it works. Okay, so whenever you um, when you convert variables, you need to add some transformations which are described by this Jacobian. So let me go through the next sections, the next page, to show you to finish off this uh, transformation. Okay. Okay. If we apply all the approximations to each of these small pieces, then we could have the double integral of r, okay, for this r, the right one. We could say that we have xy and dA. Right? We could take the Riemann sum. Okay, and then it is supposed to be approximate. So approximately, and change xy into a function of up. Right? And then dA will be Jacobian. And delta U, delta V. And then this will be equal to integrations, and it becomes S, F, G, U, V, H, U, V. Jacobian. Okay. So what's the assumptions? Okay, suppose the transformation is a C1 transformation. Whose Jacobian is non-zero. And T maps a region S in UV plane onto region R in XY plane. Suppose F is continuous on R and R and S is either type 1, type 2 double integral situations. Type 2 regions. Suppose T is 1 to 1 except at boundary S. We could write this as R, F. Maybe too small. We can make it bigger. So this theorem, it says that if you want to change from um, if you want to change, if we want to change integral in x, y to integral in u v by expressing xy in terms u v and writing the a is Jacobian okay. So this means that we want to make conversions from the xy into uv. So all the terms for xy change into uv. Okay. I will give you an example. Okay, now as example, I would love to start with the polar coordinates, just to give you a connection. Let's say we need to transform from S to R, okay, from S to R. So we see that we define all the A, B, alpha, beta, and we have the polar sections here. If we remember that the x is, we say in the function of r theta, x is r cos theta, right? And y is r sine theta, right? First, we write the Jacobian. This is dou x, dou r, dou x, dou theta, dou y, dou r, dou y, dou theta. So we take a partial derivative for x to r. This will be cos theta. X to theta, this will be minus r sine theta, right? And dou y, dou r will be a sine theta. Differentiate to r. Differentiate through theta, this will give you the r cosine theta. And we say, using this determinant, we could have r cosine squared theta minus r minus r sine squared theta, or this is r cosine squared theta plus sine squared theta, which is just r. So our Jacobian is just r. So the theorem gives us let's say if you have this double integral, then we will have this as s and f change all through conversions from xy to r theta, and Jacobian dou x dou xy dou r theta and the r d theta, and this will be equal to alpha beta a b f r cos theta r sine theta. This will be r dr d theta. So through these Jacobian formulations, we could convert and find the connections between these Cartesians and the polar. Okay, I believe in more practical way in the applications, how we are using this Jacobian formulation is pretty simple. It means that you are basically changing a new variable, changing a variable to a new variable. And how we define each integration or each region, it's based on how they relate between these two variables. How they relate, for example, x, y, and relates to u, v. Okay. And through that connections, we are having um, our Jacobian formulations. Let me give you another formula next Friday. Okay, we will give you some other example, other exercise, and also other exercise as well from chapter 15. Okay. I think I'll just stop until this part. Okay, I hope it's clear. We still have one more little sections, change of variables in triple integrals. It should be similar to double integral with different, just taking on the order three by three in the determinant. In double integral you have this 2 by 2. In triple you have 3 by 3. But I will give you the part on Friday. Um, do you have any questions so far? Okay, so basically, using these Jacobian formulations, I think will help you to determine the Jacobian in polar, in the sphere. If you forget what's the Jacobian is, you can try from the scratch by using this formulation, and later in the triple integral. Okay. Okay, if there's no questions, I would just like to end the lecture today up until here. I will do some small review next Friday to make sure that we are having the same understanding on this Jacobian. At least to know that the Jacobian is based on this determinant formulation, okay, the Jacobian. Okay, if there's no other questions, then I would like to end our lecture up until here. I will have more sections next Friday and some examples. So hope we can finish this week. Then next week there will be no class, and I will just maybe adding more additional videos for you. Okay. Okay. Maybe if you need the QR code, let me give you here. Okay, and if you have scanned the QR code, then you can leave the meetings. And thank you for joining the lecture.